After looking at systems made up of independent elements in various configurations, let's switch gears and look at the simplest possible system with dependent elements, and that's what you see: dependent active parallel with just two elements. So it's a 1 out of 2 active parallel system. The two units are identical. They're also exponential in nature, meaning that their time to failure is exponentially distributed. When both units are up, the failure rate of each is lambda. However, if one fails, because the other one, the surviving one, has to bear a higher load, presumably, its failure rate increases to lambda prime. So with that information, we need to find out the system reliability, and as an added item, the mean time to failure. So let's take it step by step. We need to recognize in the beginning that this problem is symmetric in T1 and T2, and a fact which will be useful very soon. So let's say that one fails first, and we know that then the distribution of T2 changes from 1 governed by lambda to 1 governed by lambda prime. So let's say T1 fails at an arbitrary instant tau. So before tau, T2 is same as before with rate lambda, exponential with rate lambda, and after tau, T2 is now another exponential with rate lambda prime. So if we want to expand these exponential forms, we have to do it carefully. Before tau, there is no problem. T2 has the exponential form with lambda. Element 1 is still working. But when element 1 fails, then we have to develop the second line of that f T2 given T1 carefully. The first exponential term basically says that the clock is reset. So T2 minus tau is the resetting with a new rate lambda prime. But the second factor, that exponential minus lambda tau, that comes at the end of that line, that is to ensure or acknowledge the fact that T2 can only do what it's supposed to do after element 1 fails is if it itself survives up to that time. So the probability that it survives, element 2 survives up to tau, is that second factor, exponential minus lambda tau. Now let us just put some more events in the mix. So fi is the failure of element I, so we have f1 and f2, and there are two sequences in which the system can fail, and that's where the symmetry is going to come in helpful. So either f1 then f2 or f2 then f1, and the problem is symmetric, so we'll just take the first sequence. So f1 fails first, then f2, and that's what on the left the conditional distribution actually pertains to that sequence, f1 then f2. So let's expand the event that f1 then f2. That basically means that T1 is obviously less than small t, but more importantly, capital T1 is less than capital T2. So element 2 fails second. That is very important. And the third event in that line, T2 less than little t, is that the second element also fails. And that's how at time t that sequence happens. So f1 then f2, and the system fails at time t. Now we can bring in partition in tau, and we are going to use theorem of total probability next. That should be obvious by now. So we fix T1 at all possible values tau up to t, because the system fails at t. And then we combine the limits on t2, on capital T2. On the left it is tau, and on the right it is t. So next we apply theorem of total probability, and so the integral looks like this. The first term, p within brackets, that is conditioned on t1 taking value tau, and then the density of t1 at tau, and the conditioned event is t2, the random variable t2 is between tau and small t. So if we do the algebra carefully, it is the difference of the CDFs of t at those two different times, and the answer after some algebra comes down to what you see on the screen. And if lambda prime is twice lambda, then we have to have a slightly different form, which you'll see in the next slide. So F1 then F2, that sequence has the probability that we just derived. Now this is where the symmetry is going to be useful, that the two sequences are equally likely. So the FSys, the system failure event, is the union of F1 then F2 or F2 then F1, and they are obviously mutually exclusive, so we can add the two probabilities, and it's twice because of the symmetry. And that's what you see in the end. One special case is lambda prime is twice lambda, so you have a slightly different form there. And then let's find the second task that we were given, is find the mean time to failure of the system, and we can do the integration, the area under the reliability curve. So 1 minus PF sys is R sys, so we integrate that, and the MTTF comes to 1 by twice lambda plus 1 by lambda prime. And again, we looked at the case where the two units are independent in an active parallel system, and we remember that the mean then was 1.5 lambda. Sorry, it was 1.5 the element mean. So it would be, so if lambda prime and lambda were equal, it would be 3 by 2 times 1 by lambda. There is a typographical error there, so it's 3 by 2 times 1 by lambda.